Um, Absolute age of rocks. Recall from lesson 2 that you have a relative age. You might be older than your sister and younger than your brother, or you might be youngest in your family. You also can describe your age by saying your age in years, such as I am 13 years old. This is not relative age, it is your age. In numbers, your numeral age. Similarly, scientists can describe the ages of some kinds of rocks numerically. Scientists use the terms absolute age to mean the numeral age in years of a rock or object. By measuring the absolute ages of rocks, geologists have developed an accurate historical records for many geologic formations. Scientists have been able to determine the absolute ages of rocks and other objects since the beginning of the 20th century. This is when radioactivity was discovered. Radioactivity is the release of energy from unstable atoms. The image in figure 13 was made using X-rays. How can radioactivity be used to date rocks? In order to answer this question, you need to know about the internal structure of these atoms that make up elements. Atoms. You are probably familiar with this periodic table of the elements, which is shown inside of the back cover of this book. Each element is made up of atoms. An atom is the smallest part of an element that has properties of an element. Each atom contains smaller particles called protons, neutrons, and electrons. Protons and neutrons are in an atom's nucleus. Electrons surround the nucleus. Isotopes. All atoms of our given element have the same number of protons. For example, all hydrogen atoms have one proton, but atoms can have different numbers of neutrons. The three atoms shown in figure 14, all hydrogen atoms, each has the same number of protons. One has one neutron and the other has two neutrons. The three different forms of hydrogen atoms are called hydrogen isotopes. Isotopes are atoms of the same element that have different numbers of newtons. Radioactivity decay. Most isotopes are stable. Stable isotopes do not change under normal conditions, but some isotopes, radioactive isotopes, decay, or new stable atoms. Radioactive decay is the process by which an unstable element naturally changes into another element that is stable. The unstable isotope that decays is called the parent isotope. The illustrate an example of radioactive decay. The atoms of an unstable isotope of the hydrogen parent decay into atoms of a stable isotope of helium daughter. Figure 14. All forms of hydrogen. Figure 13. The release of radioactive energy can be used to make an X-ray. Figure 14. All forms of hydrogen contain only one proton regardless of the numbers of neutrons. One proton, 0 neutrons. One proton, 1 neutron. One proton, 2 neutrons. Figure 15. An unstable parent hydrogen isotope produces the stable daughter helium isotope. The extra neutron in hydrogen 3 makes it unstable. The extra neutrons decays and forms a proton. In the process, a new stable forms. Stable helium -3 nucleus. When the neutron decays, energy is released. Half-life of radioactive decay. Figure 16. The half-life is the time it takes for one half of the parent isotopes to change into daughter isotopes. Object contains 100% parent. 2. One half-life, 50% parent and 50% daughter. 3. Two half-lives, 25% parent and 75 daughter. 3 half-lives, 12.5% parent and 87.5% daughter. Figure 18. The half-life is the time it takes for one half of the parent isotopes to change into the daughter isotopes. Half-life, the rate of decay from parent isotopes into daughter isotopes is different from the different radioactive elements, but the rate of decay is constant for a given isotope. The rate is measured in time units called half-lives. An isotope's half-life is the time required for half of the parent isotopes to decay into daughter isotopes. Half-life of radioactive isotopes range from a few microseconds to billions of years. The graph in figure 16 shows how half-life is measured. As time passes, more and more unstable parent isotopes decay and form daughter isotopes. This means the ratio between the numbers of parents and daughter isotopes is always changing. When half of the parent and daughter isotopes is always changing, when half of the isotopes have reached one half-life, at this point 50% of the isotopes and parents and 50% of isotopes are daughters. After 2 years, 2 half-lives and 1 half of the remaining parent isotopes have decayed so that only 1/4 as much parent remains as the start. At this point, 25% of the isotopes are parents and 75 are daughters. After 3 half-lives, half again of the remaining parent isotopes have decayed into daughter isotopes. This process continues until nearly all parent isotopes have decayed into daughter isotopes. Radiometric ages. Because radioactive isotopes decay at the constant rate, they can be used like clocks to measure the age of the material that containing them. In this process called radiometric dating, scientists measure the amount of parent isotope and daughter isotope in the same of the material they are to date. From the ratio, they can determine the material's age. Scientists make these precise measurements in laboratories. Radiocarbon dating. One important radioactive isotope used for dating is an isotope of carbon and radiocarbon. Radiocarbon is known as carbon-14 or C-14. Because there are 40 particles in the nucleus, 6 protons and 8 neutrons, radiocarbon forms in Earth's upper atmosphere. This is mixes in which a stable isotope of carbon called carbon-12 or C-12. The ratio of C-14 to C-12 in the atmosphere is constant. All living things use carbon as they build their repair tissue. As long as an organism is alive, the ratio of C-14 to C-12 in its tissues is identical to the ratio in the atmosphere. However, when an organism dies, it stops talking in C-14. The C-14% in the organism starts to decay to nitrogen-14, N-14. As the dead organism's C-14 decays, the ratio of C-14 to C-12 changes. Scientists measure the ratio of C-14 to C-12 in the remains of the dead organisms to determine how much time has passed since the organism died. The half-life of carbon-14 is 5,730 years. That means radiocarbon dating is useful for measuring the age of the remains of organisms that died up about 60,000 years ago. In older remains, there is not enough C-14 left to measure accurately. Too much of it has decayed to N-14. Figure 17. Scientists determine the absolute age of an igneous rock by measuring the ratio of uranium-235 isotopes parent to lead-107 isotopes daughter in The rock's minerals. An unstable plate's parent isotope U minus 235 will decay at a constant rate and form a daughter product Pb minus 207 after one half-life. Its concentrations of a parent and daughter isotopes are equal. The parent isotopes will continue to decay over time. After two half-lives, 4/1 of the original parent remains. After three half-lives, 1/8 remains, and so on. Dating rocks. Radiocarbon dating is useful only for dating organic material from once living organism. The material includes bones, wood, parchment, and charcoal. Most rocks do not contain organic material. Even most fossils are no longer organic. And most fossils, even tissue, have been replaced by rock-forming minerals. For dating rocks, geologists use different kinds of radioactive isotopes. Dating igneous rocks. One of the most common isotopes used in radiometric dating is uranium minus 235, or U minus 235. U minus 235 is often trapped in the minerals of igneous rock. They crystallize from hot mountain magma. As soon as U minus 235 is trapped in a mineral, it begins to decay to lead minus 207 or Pb 207 as shown in figure 17. Scientists measure the ratio of U minus 235 to Pb minus 207 in a mineral to determine how much time has passed since the mineral formed. This provides the age of the rock that contains the material. Dating sedimentary rock. In order to be dated by radiometric means, a rock must have U minus 235 or other radioactive isotopes trapped inside it. The grains in many sedimentary rocks came from a variety of weathered rocks from different locations. These radioactive isotopes within these grains generally record the ages of the grains during the time when the sediment was deposited. For this reason, sediment rocks is not as easily dated as igneous rock in radiometric dating.